Let's take a look at the square root of 5 squared. 5 squared is 25. And then if we square root that, we'll have 5 again. Now I know some of you might have already figured out what's going on here, but let's try one more example. What about the square root of 7 squared? 7 squared is 49, and then we're going to square root 49, so we're going to be back to 7. At the end of my last lesson, I gave you guys some examples to try. One of them was this one, the square root of -4 squared. Now the answer to this question is actually +4, not -4. But that's only because the square root function only calculates the principal square root, something we covered 2 lessons ago. Otherwise, when we're dealing with non-negatives, which is more common, because the square root is an inverse function of the square, if we square a number just to square root it again, we're going to have the same number we started with. The only exception is when it's a negative number, in which case we'll have a positive version, because like I said, the square root function only generates positive solutions. Now this works the other way around as well. If you square root something like 9, only to square it again, we're going to be back to 9. So these two functions will literally cancel each other out. I want you guys to keep this in mind today because we're going to be looking at fractional exponents, which means we're going to be doing a lot of this inverse functioning thing. Buckle in! Let's start with something like 9 to the power of a half. What do we do if we get 9 to the power of a half? We've learnt the zero exponent rule, the negative exponent rule, but this is new. Let's see if we can use what we know to take a crack at it. Remember this chart I made earlier? This is a very useful tool for demonstrating the relationship between the size of the exponent and the number it creates. But in our example, we had a base of 9, so we're going to go ahead and change this table to base 9. There we go. Okay, so 9 to the power of 0 is 1, and 9 to the power of 1 is 9. Just looking at this, we know that 9 to the power of a half has got to be somewhere between 1 and 9. Now your first instinct might be that if a half is right in the middle of 0 and 1, then 9 to the power of a half should also be right in the middle of 1 and 9, so 5 or something. But here's the catch. Remember that exponential relationships don't follow a straight line, they curve. If this was a linear relationship, taking the midpoint between 9 to the power of 0 and 9 to the power of 1 would make perfect sense. But exponential relationships aren't nice straight lines, they curve, and the further they go, the curvier they get. 9 to the power of 2, for instance, is nowhere near the midpoint between 9 to the power of 1 and 9 to the power of 3. Okay, so we don't know what 9 to the power of a half is, but we've learnt 4 different index laws now, so let's plug in a few and see if we can make sense of this. The index law for multiplication tells us that a to the power of m times a to the power of n is equal to a to the power of m plus n. In other words, if you're multiplying index numbers with the same base, you can just add the exponents. We don't know what 9 to the power of a half is, but what if we had 9 to the power of a half times another 9 to the power of a half? Well, according to the index law we were just talking about, we would get 9 to the power of a half plus a half equals 1. In other words, 9 to the power of a half times 9 to the power of a half is equal to 9. Does this look familiar? 2 identical numbers multiplying to make 9? You're right, this is the square root of 9 all over again. 3 times 3 is equal to 9. The square root of 9 is 3. 9 to the power of a half is 3. Now we're on to something. Well, if this is true, if these are equal, there's more than one way we can prove it. Remember how I showed at the start that if you square root 9 only to square it again, we'll come right back to 9? So we can test this with 9 to the power of a half. If 9 to the power of a half is really the square root of 9, then the square should cancel out the half just like this square cancels out this square root. We've learned the index law for powers, so we can check this to see if it's actually true. All we have to do is multiply the exponents. 9 to the power of a half squared would be equal to 9 to the power of a half times 2, which is 1. So 9 to the power of a half squared is equal to 9 to the power of 1. Yes! It works! Let's try another example. 8 to the power of a third. If we follow the same logic, 8 to the power of a third times 8 to the power of a third times 8 to the power of a third should give us 8 to the power of 1, because a third plus a third plus a third is 1. If we're looking for something that multiplies by itself 3 times to get 8, what are we looking for? The cube root of 8. There's another website you can go on, which I'll link in the description below, that uses the analogy of a machine called the Expand-O-Tron that makes numbers multiply at a rate of your choice. Imagine you have a machine that you can put the number 1 in, and you can select how long you grow it for and how fast you grow it. If you choose a multiplication rate of 9 and grow it for a certain number of minutes, then every minute it will multiply by 9. So if you put it in for 2 minutes, it will multiply and come out at 81, because 1 times 9 times 9 is 81. Imagine you plug it in though and select a rate of 9, which means every minute it will multiply by 9, but you only put it in for 0 minutes. Well, then it's not going to change. It will still stay at 1. That's another way of showing how anything to the power of 0 is 1. Because no matter what your multiplication rate is, if you don't actually give it any time to expand, it will just stay at 1. And if you plug it in and choose a rate of 9, but then you twist the dial the other way and go into negative time or back in time, then instead of seeing your number grow every minute, it's going to shrink. It'll shrink by the same factor though. Every minute it will be 1/9 the size it was before. And finally, imagine you plug it in for 1 minute, but then you take it out when it's only half cooked. Now you might be thinking that after 30 seconds the number 1 will become a number 5, right in the halfway point between 1 and 9. But remember, the Expand-O-Tron multiplies. With every time increment, it's multiplying. It's not adding. It's not adding 4 and then adding another 4 to get to 9. It's constantly multiplying. After 1 minute, it's 9. After 2 minutes, it's 81. After 3 minutes, it's 729. So you have to think about it like this. If every minute it's multiplying by 9, then what must it be multiplying every half minute, every 30 seconds? It has to be 3. Because the only way you're going to get a multiplication rate of 9 every minute is if every half minute, every 30 seconds, is multiplying by 3. So that 3 times 3 is 9. So when you take it out after 30 seconds, it will have only multiplied to 3. And then when you put it back into complete, it will multiply by 3 again in the same amount of time to get 9. I hope that either one of these explanations makes sense to you. Like I said, this is the trickiest concept to grasp with index numbers. If you're able to understand the way I explained it earlier, then that's fantastic. If you like the Expand-O-Tron idea, there'll be a link in the description if you want to read more about it. It is pretty neat. Take your time with this and try playing around with Desmos as well if you learn better by seeing a visual or graphical representation of fractional exponents. If you want the rule though, here it is. A to the power of 1 over n is basically another way of writing the nth root of a. So 9 to the power of a half means the square root of 9. 64 to the power of a third means the cube root of 64. What this means is, if you want to find, say, the 11th root of negative 177,147, we could write this as negative 177,147 to the power of 1 over 11. And this is what we'd put into the calculator in order to find the answer. Try a few questions on your own. Convert these radicals into index form and then input them into a calculator to find the answer. I hope this video hasn't completely traumatized you guys. I know this is a hard concept. There's just one more level to fractional exponents that I won't be covering today because this video has gotten long enough, but the next video shouldn't be nearly as long. So, like always, I'll leave you guys with a final question. 9 to the power of a half is easy enough, but what if we had 9 to the power of 3 halves? What would that be? Try using the same techniques I used today to see if you can figure this question out. Try breaking up the fraction into halves, or 3 times a half. Think you can figure out the rule? Come back next time, see if you got the right answer, and as always, thanks for watching at Sneezy Teachers.